Hello, welcome to the last meeting of the New England Dynamics and Number Theory seminar for the spring semester 2024. And we're very happy to actually have a speaker from New England. We haven't had this luck for a while. And today we have Alena Erchenko from Dartmouth talking about flexibility and rigidity for Cantor repellers. Welcome, Alena.
Okay. Thank you very much for invitation and giving opportunity. I just moved to Dartmouth last summer, so new
Yes,
to New England.
welcome to New England.
Thank you. Yeah, and today I would like to tell about the work with Jacob Mazor. He is a graduate student at Stony Brook. So we were trying to explore like Cantor repellers, but before I tell you like the general definition, so let me think just about the example and kind of build up like what type of questions we kind of were interested about. Okay, let's look at some map, which is defined on a finite number segment. So here there's like two segments, right? And into 0, 1, and on each segment in this situation it's very easy, like just multiplication by 3, it's on to 0, 1. And okay, we want to understand what this map is doing, for example, and so what you do, okay, we want to iterate our dynamical system, we want to find an invariant set, right? Okay, so we'll look for invariant set, and okay, we understand that we want to, what is an invariant set? So that the preimage of the set is set itself. And so basically what we want to understand what is the intersection of all the preimages, right? Like, so I have, I kind of want to look, if I look at the 0, 1, and I look at all the preimages of it, infinity, this is my candidate for my set, right? Okay, so let's see like what's happening. Okay, first we look like the first preimage of 0, 1, and remember how it was defined. Here, okay, we see it's 0, 1 third, 2 thirds, 1, right? But then we'll continue doing this, and maybe you already know what the answer would be, but kind of I'll get kind of like 2 thirds parts of the first segment, 2 first parts of the second one, and I can keep doing it, and actually would be continuing. And what you probably recognize already is kind of my lambda in the situation, if I take the whole intersection, would be a middle Cantor set, right? So I do have an invariant kind of nice set here. Okay, it's classical example, right? But let's kind of look from the point of view. So what we can say about lambda or f on this lambda set, right? On our invariant set. So first we can say, okay, I got this invariant set. It's not the whole interval 0, 1, so but how large it is, right? And we can understand the largeness in the sense of like Hausdorff dimension. So let me maybe recall, just in case, the definition. So we fix some scale, right? And for each number alpha, so for each alpha greater or equal than 0, we can consider kind of a number, trying to compute a number, we want to see how large lambda in some sense. And how we do this, we look at the cover. So cover of lambda, but of small size like exactly this delta. So we assume the diameter of all ui is less than delta. And this can be kind of finite. We can look at the countable one the way. So countable one. And we look, okay, we want to measure this cover. So we take diameters of each ui, but with the weight kind of to the power alpha, 1 to infinity. And then, okay, we want to cover by smaller and smaller pieces. Okay, so we'll take a limit when delta goes to 0, and we get in a number assigned like to lambda, kind of measuring how what's its weight. And it's actually true that depending what it might be kind of, there are some kind of breakout points, so it's either infinity, it's or it's zero number actually, or there might be a finite number where it might be infinity or zero, actually might be like some finite number. So this is exactly this break point we exactly will call we're calling Hausdorff dimension, right? So let me write this way, kind of it's infimum where this number is zero. So the behavior, as I said, like kind of this infinity, zero here, and at this point it's kind of not clear. So this is our kind of dimension. Okay, so this is like general definition. So we can say, okay, but what it is in our situation for our map or our middle Cantor set. Okay, and we can do this kind of, I would don't do like rigorous proof, but if we think about, say, delta of roughly of size 1/3 to the k, right? I kind of like, we need to produce the covers, small covers, right? Those intervals are kind of exactly our nice covers in some way, right? Okay, they're not kind of, they're segments, not open sets, but you can wiggle a little bit, like making it rigorous. So if delta of size this, then basically we need 2 to the k intervals of size, okay, roughly this 1/3 to the k to cover my lambda, right? And so if I do try to compute h alpha delta of lambda, it's roughly is 2 to the k divided by 3 to the alpha k, right? And then saying that my delta goes to 0, which would mean like my k goes to infinity, right? I can see that there's exactly a break point. I can observe the way that, because if my alpha is bigger than log 2 over log 3, is a 0. Otherwise, okay, if in other situation, if alpha is less than log 2 over log 3, this is plus infinity. So that's why I know that from this definition, I kind of ran out of space a little bit, but I have here the dimension of my invariant set for my example is exactly log 2 over log 3. Okay, it's not fully rigorous proof, but roughly the idea how you do it. Okay, so we can talk about the size of the invariant set. And for this example, we could actually calculate very carefully. Then we also can notice a little bit more that this dynamical system is actually topological conjugate to the shifts on to the left shift, right? Because like each of those basically segments here, 0/1 here, it's kind of basic and give me a coding like kind of 0, 2 in which parts like I'm ending up, right? And doing that, I exactly get the coding, and so I see a topological conjugate, and I can look at the complexity, exponential complexity of orbit segments, which is topology like total complexity, right? Then their topological entropies have to coincide, and we know like, okay, for the shift it's a log number of symbols we use, like, right? So in this situation it's log 2. Okay, so we can say already like those quantities we could calculate quite precisely. Next question, you can try to see, okay, what invariant measures do we have in this situation? And okay, kind of what are interesting invariant measures, so which can be question who thinks which ones are interesting measures, but some of the classical examples, we know that we can look at the metric entropies, right? My dynamical system, which I'm kind of looking through the prism like of the measure, thinking like which orbit segments I'm counting, right? And so if I take, we have a variational principle, which tells if I look the supremum, this is exactly my topological entropy, right? It's my variational principle. And in some situations, and in our ideal nice, we have uniform expansion, everything nice. We know that there is a measure which attains the supremum. And so this is what I'll be denoting MME, so measure of maximal entropy. And so it's exactly the one, my topological entropy is equal to H MME of F. And here, so we have this invariant measure, and here it's quite, especially with the coding scene, like we actually understand the measure of maximum entropy quite well. So if you kind of start looking at the pre-images here, right? Okay, I'm looking on my set, right? But like the part of my invariant set lies in here, so it's exactly would be for the part sitting here. If the whole part sitting here, it would be one half, right? It's equal weight gives to those. And if I'm going here, it will be 2 squared, right? And so on, the same here and here and here. So I kind of like see the weights on each level. So on each level, I actually do know what this measure assigns. So kth level basically gives me weight 1 to the k, if I'm looking at my invariant set. So I quite understand there is nice invariant measure, but not entropy of it, it's actual topological entropy. But there is also another measure. Okay, secretly, maybe, you know, it would be the same, but let me kind of present it differently, at least for this, because generally, when we will be talking about Cantor repellers, there might be different measures and behaving differently. So I want to look at the measure which has kind of what's called conformal measure and find an invariant measure. So here I've denoted H dimension H lambda. So it's exactly our, remember, our definition here, right? And actually it's finite in this situation. So it's nice. And so I don't get 0 infinity. So like actually measure, and it's conformal in a way that because if I try to compute lambda, if I try to compute the measure of the set f of a, where on a my map is injective, I have, so it's in one of the parts living 0, 1/3 or 2/3 1. So what's happening that I can compute that it's equal to the integral of a of my derivative and exactly in this power of my dimension of my invariant set d okay, yeah, with respect to with respect to this measure. Okay. So so there is this exactly this kind of conformality. So it's what's called, you can say, dimension H lambda conformal measure. And so I have this, and it's not only just conformal measure with this nice property, but because alpha, which I use this dimension H lambda, it's actually has a nice Hausdorff dimension. So we can define for any measure, we can define its dimension, which would be just by definition just infimum of dimension of the full measure sets, right? And so what we see here, that if we do this job for this conformal measure, which we have here, then this is exactly the dimension of my invariant set. So in some way, what you can think about this is kind of measure of full dimension.
Can I ask a question?
Yeah.
define two measures. One is this measure of maximal entropy, and is saying that it maximizes something.
Yeah.
And the second one is defined by also saying that it satisfies some condition. But is it clear that it defines it uniquely, both of them?
I mean, generally, it's kind of, if you're outside of the class which we're working, it's a question, say system has a conformal measure which has this property, and in some situation might be not unique, but with uniform expansion, like
Okay.
nice
Okay.
situation would
So
be unique.
in general, the dynamical system doesn't have to have.
No, it doesn't
Okay.
have to have it and might not have one. And yeah,
Okay.
it's a lot of questions. So it's
Okay.
kind of like good a lot of people like studying like all those Hanon maps and everything, how they behave, rational, like in complex dynamics, especially like all this, do you have a conformal maps, conformal measures there and how many? Yeah, so here definitely uniqueness is by uniform expansion given. As usual, kind of our and also situations nice, and also for uniform expanded situations are nice.
Mhm.
Any other questions? Okay, so although I presented like this differently, but because here the expansion everywhere is ×3, you actually can notice that MME does have this property. And so in this situation, those measure full dimension, which let me call it the MFD kind of. So in this situation, actually happened that measure full dimension is equal to the measure of maximal entropy. And actually, it's kind of just two different descriptions. But I mean, natural question, is it always the case? And the answer is not, as we'll discuss in a little bit, but just happened here. But I want to have you like two pictures kind of like of different way of thinking about that measure. Okay, so we have here invariant measures. So in the last kind of, I mean, you can look at a lot of like invariants kind of or information about system, but let me kind of the last piece of information to stop here is look at the Lyapunov exponents. So I have my two measures which I'm looking at, my MME, my measure of full dimension, and so I want to look at Lyapunov exponents. Okay, I didn't say, but let me maybe say, I'm having here a condition like ergodic, right? And so invariant subsets, invariant sets of measure 0 or 1, right? Of measure 0 or 1 for those measures. And those measures which we constructed here, those are ergodic. So let me make maybe in color, both are ergodic. Okay. You have to prove it. I'm kind of more like summarizing what we know here at this moment. Okay, and so if ergodic, so I could have given a definition of Lyapunovs in general, but if I have ergodic measure, it's actually kind of very easy because it's constant with respect to measure would be constant because like expansion would be constant almost everywhere with respect to measure. So I can actually assign a measure. And so if I look at my map and have measure ergodic, then I just integrate log of my derivative, right? My expansion. And in this situation, we see, okay, my derivative is everywhere was 3, right? I'm so far still talking about this example. That's kind of all the definition I think might be good to think about, like on the example. So here it's all 3. So in particular, I would see that my measure of maximum entropy and my Lyapunov exponent, because it's the same measure, but let me kind of emphasize in here, it's just log 3, right? So, but we can have this information. Okay, so about this map, we kind of covered quite a lot of information. I mean, you could have looked at others, but let me stop here. And so the question is here, okay, I can view this example as a example of the map in some class. And the question, if I look at the data which we discuss here, what happens with it? Okay, so what I mean here, so let me give you like a general definition what we call counter repellers. Now, instead of having just two intervals as we had before, I'll have a collection of D intervals. So it's my, maybe a better, I'll use the word segments, meaning closed, like here, and their segments, they're disjoint. And let me think that they're ordered in a way, and so so kind of each, maybe I better write this way, AJ, BJ, and kind of they're ordered, and I assume that my first one starts always at 0, so I kind of like fixing the endpoints. So B1, I have A2, B2, and so on, and my final endpoints I also fix, so it's 1. So I'll look at the collection similar of segments, and on each of the segments, I'm defining a orientation preserved, uniformly expanding onto map C infinity diffeomorphism. You could work with low regularity, but let me for now like things smooth all. So kind of you can see the picture, potentially a map. And so I have basically D maps, and this is what we'll call D Cantor repeller. So repellent because I'll have expansion everywhere. And degree D, it's kind of in some way you can see like how many branches I have, right? If I think about pre-images of 0, 1. Okay, so those are repellers, and actually for them we can talk about all the same things as we discussed for our example. So I have an invariant set, so I can look at all the pre-images. It's some Cantor set, so then in this situation, it can be coded by D symbols because I'm using D intervals, right? So topologic entropy would be fixed log D if I'm in the class of D Cantor repellers. And I do have for this system measure of maximum entropy and measure of full dimension. And again, measure of maximum entropy, because of this coding, I can easily understand what it is. It's assigns 1 D over K, D to the K on a Kth level. And measure of full dimension, it's not exactly this H to the dimension of this, but it's absolutely continuous. So there's a function I can get a measure of full dimension. And I can look at the entropies, I can look at Lyapunov exponents, and in this situation, we actually have some relations, I mean, which we had in the other one, but we kind of not explicitly said it. If you remember, this was exactly log 2 in the other situation, and this was log 3, right? And we exactly was getting dimensions, say, of our invariant measure. So, but in general, for any invariant ergodic invariant measure, you have this relation that the Hausdorff dimension of the measure is equal, or dimension of the measure is equal to the entropy of this measure divided by Lyapunov exponent. And again, from variation of principle, you do know that topological entropy should be greater or equal than measure of full dimension. Because we have expansion, you have to have those numbers bigger than 0, because we have uniform expansion. And also because measure of maximum entropy, its dimension is less or equal than measure of full dimension, but it can be much smaller a priori. It doesn't have to be a measure of full dimension. But those numbers, again, because of uniform extension, are between 0, 1, and there's actually strict, I don't want to say equalities, but those are strict inequalities. I want to emphasize. So we have those relations, and we actually can kind of, if we're looking at our kind of thinking that we'll only think about this invariant measure of maximum entropy, measure of full dimension, and all those associated quantities, we can try to ask ourselves, like, what relations do I know, or how freely they are, right? A priori for one measure, so I have its dimension, topologic entropy, Lyapunov exponents, and for the other one. So I have 6 quantities, but because of those relations here, like Bowen-Manning formula, we actually can realize that only kind of 3 matter. As soon as you know 3 of them, the other, you can figure it out. And just for presentations, kind of convenient to think about dimension of my invariant set, and it has to be between 0 and 1. And think about the Lyapunov exponents, because in this situation, they have to be separated by this log d over the dimension of my invariant set. Okay, so I want to emphasize, so I have here that the equalities happen simultaneously, and they indeed do. And if we actually kind of, let's me think about this one for a second, just easier, try to do some equalities, right? If we use the Bowen-Meinen formula, we would know that this is lambda measure full dimension is entropy of measure full dimension. Okay, let me skip writing with respect to lambda here, but and here I have dimension my lambda. And if the equality actually happen, if we have this, right? It's basically what I'm saying that entropy of measure full dimension is the same as topological one, right? But again, from uniform expansion, we know that measure of maximum entropy is unique, right? And this exactly will be saying that the measure of full dimension is measure of maximal entropy in this situation. And that would mean that I will have to have equality in this situation as well, right? So if that one is equal, then the other one is equal. In the other way, if you assume, so if we assume that log d over the dimension is equal to the lambda MME, then what we actually will be getting, again, kind of using formula, what we'll get that the dimension of the measure of maximum entropy is equal to the dimension of measure of full dimension, right? Or in a way, but actually this is applying you that MME has to measure full dimension. And here it's kind of, you need to recall a little bit other, kind of to see that, I mean, it was shown by Pritsky Urbansky, you can find as a result, but in a way, like what it uses is description measure full dimension through the pressure function. So kind of like, if you look at the kind of potentials minus T log my expansion in here, and you look at the pressure function of those phi t's, which, let me remind you, it's kind of like our variational principle, but I have entropy here plus integral my phi t, and I'm so look at the supremum here. So the one which will make P5T equal to 0, the T which generates it, if it's exactly the dimension of my invariant set, this is a way to get measure of full dimension. And kind of because the dimension coincide and uniqueness of measure of full dimension, you can derive it. So roughly the idea, so you can obtain this. And so we do know now the equalities happen simultaneously. We know those relations. So one of the questions would be, are those all the restrictions we know? And what we answered with Jacob, that yes, it's indeed. So what we mean is they're flexible within, if you give me 3 numbers, A, B, C, such that my A is between 0 and 1, and my B is less than 0, so less or equal than, I mean, equality always can make, like, just make a constant expansion. So we're kind of basically interested in the case when you don't have the equality. So let me make it log d over the dimension, which I should be having dimension. So let me over A, and this is less or equal than C. So I have numbers A, B, C such that then we can find F d Cantor repeller, so that I exactly have my A, my dimension. So let me not rewrite it. So this will be exactly A, this exactly would be B, and this would be exactly C. So I can prescribe any numbers as long as they satisfy those relations. I can find a map which would have those parameters. Okay, so this is what flexible. So one question kind of naturally could be, so we're producing some counter repeller with here, but what you could have asked, can I do a little bit more? So let me maybe write a question. Can you do the same, but also fix lengths of ii's? So remember what those ii's, it's those intervals. So for now, what we're doing, we're kind of choosing freely what those guys would be. We only think about the parameters, but the natural other question, can you do with a little bit more restriction? So you're given the lengths, d intervals, and you want to construct there with those parameters. Currently, we don't know the answer. There's something plausible that the answer might be still yes, by the way, but it's an open question. Can you do a little bit more? Okay, so this is kind of what we would call like flexibility result. So let me say a little bit about rigidity. I kind of a little bit already mentioned this result by Pristiki and Urbansky, saying that if dimensions are the same, then MME coincide measure full dimension in this situation. But what we try to explore, like as usual, like we try to kind of classify, right? So it's only that measures, we say we have information about measures, but the question is, can we say something about our map? And kind of always kind of from, if you think about situation of uniformly expanding maps of degree d on a circle, right? There's nice classification. So you're conjugated like to one of those guys. So we was trying to explore the same ideas. Do we have like just a linear model here that we're conjugated to? And so what we explored that you indeed have conjugacy, but the regularity is different. So let me maybe say before I kind of actually talk through the results. So what I mean by conjugate is, so I have my F and it's defined on some invariant set, right? And I have my G, it has its own invariant set, right? In here. And the idea when we talk about conjugacy, what we would want to actually, we would want to look at the neighborhoods of lambda f and lambda g, and let me call them uf, ug, and ug. And actually, my conjugacy would be on those, defined on those neighborhoods. And so then I can talk in our regular sense what means Lipschitz and C infinity and so on, right? So, and depending on what it is, so it's conjugacy, if kind of it's one more requirement, I will ask it to be orientation preserving. Might be not like as near, but kind of otherwise you have more options how, but we would want to like orientation preserving here. And so it's conjugate, so let me, so I have its correct order. So F, if I take FH and I have here my HG, right? So that it's conjugates and it's a homeomorphism, right? So at least homomorphism, so it's invertible, and regularity exactly, so can be CR, then we'll say here CR conjugate. If Lipschitz, then we say in here Lipschitz. So depending on what we're defining. And so what we got here with Jacob, can we try to explore this question, what we have, we always can actually, if it happens that we are in a situation kind of measure full dimension coincide with measure maximal entropy, what happens that we can find a conjugacy, but only Lipschitz conjugacy to a linear model. So the way kind of, let's say, times 3, like if it happened like was there, I mean, it was already linear mod, but something like this one, looking like on each intervals will be just multiplication by a, okay, appropriately linear map, so it's onto 0, 1. And okay, first initiative would be, can we do better? Can we do C1 and so on? But we only could produce conjugacy, C-infinity conjugacy actually, but only that my derivative on the invariant set is A. So there's no like on those intervals. And so, and actually there's a reason kind of, you can see that it cannot be C1, like write that like kind of to the linear model, because you can construct an example. So think about my F is as our first example, as at the beginning of the talk. And for my G, let me think about other map. It would be, I can write formulas, but maybe better like the picture if we think about it. So I have here 0, 1, here my 0, 1. So at 0, 1/3, it is times 3, the way like it was. But on the other part here, it's a little bit different. It's a little bit maybe not the nicest fraction, so let me, I can write the numbers, but maybe it's not as important. Can produce, let me kind of in here, so it's my 3/5, and this number is, let me double check with my notes, 13, okay, 32. Okay, there are some fractions, so just to make it like that it's expanding. And there's one more here, it's 13/15. But what's more important here, so it's times 3 here, and it's times 3 here. And here it's something like which glues it like nicely, but the derivative here is still like bigger than 1. So if you look at the pre-images, you kind of basically, where I drew this the green one, you kind of forget about this interval eventually, so it disappears. So at the end of the game, your expansion, your invariant set will still be times 3. But on the way, you will not. But if you try to look at this example, those F and G are not C1 conjugated. They cannot be, because you kind of basically can do by contradiction, assume they are, and you basically see that around 0 point, you have a problem, because you actually, for this explicit example, you can exactly see which points go to where, like the points of form 1/3 to the end, where they go, or where the points of the form like 1/5, like from the 3/5 coming, kind of where do they go as well. So it's kind of like, and you cannot make them C1. Okay, so the next thing, okay, they're not C1, but maybe candidates, okay, what you can notice here, there's an interval here, right? Like it's kind of eventually linear multiplication by the same number, right? And so we kind of can give a definition of eventual linear. So on some level, I'm just expanded by that number. If you don't look at my question for a second, but you could have asked, okay, maybe they're all C1 conjugated to those models, but it's not true. So it's not like all of them. Why I'm asking here for the criterion, because in general, it's not true. And it's a work by Shannon, Benavide. Okay, I'm not writing the right order. Let me, Benavide, Rodriguez Hertz, and here I mean Federico Rodriguez Hertz, and Mario Shannon. So they showed that not always. So they show the examples which are not C1 conjugated to those eventually linear. So in natural question, and you can ask, when they are. So what might be special about those maps? Okay, so let me kind of say maybe some more open question. We were coming up this pressure, right, in our geometric potential. This is the name, kind of geometric potential. There was coming up like kind of like description, measure full dimension, and measure of maximal entropy. And basically all this data, which I talked about, Lyapunov exponent, dimension, topologic entropy, this data is partially encoded in, this data is encoded in the pressure. Pressure carries more information, but kind of basically what we said, like with Jacob, in some way you can think about that, we just showed that at those points, first of all, like my blue one can slide, right, because of dimension, but I can realize any slopes, right? That's what we basically showed in the class of fixed D Cantor repellers. And the natural question becomes then, oh, okay, I can do this information, but maybe I can do all this information, right? So the question is, what pressure function actually can occur? I mean, we know some rules that it has to be like analytic, has to be convex and everything, but kind of what the full list of the properties of the pressure function. And it seems like it's quite non-trivial question in a way, because it seems there's more probability restrictions than we expect. And some of them kind of, there's work by Mark Policott. It's not exactly in the setting. It talks about in a case of full shifts, like for example, the full shift of finite type, they showing that there's some relation on second, third, okay, second, or maybe better, instead of listing this, there's some relation. So if this is my function pf of t is a function, so I can think about function of t. So there's of my second and my third and fourth derivatives with respect to t. So it's, if I'm thinking this is a function of t, so they actually produce an expectation probably like similar relation should be exist in our case. And also like there's work of Kucherenko and Kwas where they study and also for diffeomorphism on tutors, and kind of you can ask a similar question, and they also produce different type of like restrictions. So basically it comes like what our pressure function can be. And with respect to this, it's quite interesting maybe to mention another work of Kucherenko Kwas, where they actually, so this is for not in our series, but kind of in case of Anosov diffeo on T2, what they basically say, you can reformulate these questions by what are pressure functions, what are possible pressure functions for if my dynamics is actually just linear, so linear hyperbolic automorphism for linear hyperbolic automorphism of torus of T2, and kind of potentials and Herder potentials. What I mean, like basically, it doesn't have to look at the geometric. So they kind of like can fix my like the dynamics which I'm looking, but and just take any, maybe it's not, let me call it psi. So any Herder function, and so my t psi, look at Herder and look what is pressure is as a function of t. So if you understand those, you basically understand the one for geometric potential, like the one which we're geometrically looking like what the expansion of this map. And in the case of Anosov, it's kind of unstable expansion. So natural question maybe kind of is the similar kind of information is true for the case of Cantor repellers. Is it just to answer this question, like what are possible, do we need just kind of thinking about like ideal guy and looking at all the Herder potentials? So we don't know. Okay. I think I still have like about like 10 minutes. So let me kind of just maybe not go deeply into proofs, or maybe I should stop if there are any questions. So before I go to the proofs. Okay. If no questions, so let me kind of say like because of one dimensionality in the situation, it's more or less actually we're able to do a lot of things like by hand in a way. So it basically, but it's kind of interesting that you're actually able to do this by hand. And more or less, we kind of look at the structure of the pre-images. Basically, we need to understand what should, at some point on the level, what should happen, like what expansion I want to see. And in some way, kind of slowing down around the fixed point, you want to see kind of that your lengths don't shrink too much. So kind of like the way like your kind of measure full dimension kind of sees like slow, you want to, for example, if you want to get it like kind of behavior changing kind of so okay, maybe I should say MME is a little bit easier. Kind of MME, if you start having like very short intervals, eventually, it's your dimension of MME basically kind of goes to zero. Because you kind of you can see because of the relation. And measure full dimension, you also like from this kind of, you basically a lot using the conformality property, which I had somewhere when I described it. Yeah, it's kind of this using relation, you kind of understand how the measure from the level to level does change. And so we're basically playing with these parameters, kind of how the expansion goes, and kind of put it like in different spots. And we see that basically, I mean, we have like several parameters here, alpha, beta, S, and R. There's some relation between them, but just varying those, we're actually able to produce everything. So we actually kind of, in a way, what we are working, do work with eventually linear ones. We actually showing more. So we can realize all those values already with eventual linear, although we know that there are examples which are not conjugated to them. But this turns out, I don't know, like how helpful maybe, or no, like kind of, you can think about the graph pre-images, it's like how we distribute like the expansions among them. And okay, and basically in some way, what one thing like to keep about this Cantor repellers, that it's really important like what happens on those pre-images, because kind of there is information in between, right? Like even like our regional guy, right? Okay, there was here, but they kind of we throwed away middle thirds, right? So and all those examples like the one which I said not C1 conjugated, there is something happening here, but eventually this information kind of gets lost. You really kind of need like on the level, when you're constructing, you need to make sure when you're gluing back that you actually can keep it expanding, right? So whatever you do in the lens that you're not, it's expanding on those intervals, but you cannot go back up in a way like that it's still expanding. But as long as you're doing this carefully, you can produce. And this is more or less where all those kind of conditions come up, just to guarantee the way that we put in those expansions, we can actually construct a linear, we can eventually linear decanter repeller on there, so that you have an expansion everywhere. And I probably would not go into more details at this moment, so thank you.